Regression analysis. Today is going to be regression, and this is really my favorite topic. Those of you that are still working on the quiz, please try to ignore me. Shouldn't be too complicated. Okay. So we have regression basically as a continuation of correlation. So we have this correlation where basically we have a tool that establishes an association between two variables, and regression basically builds on that. We have with correlation, as we remember from chapter 15, we have a tool that basically establishes a correlation between two variables by basically establishing with a standardization step that we have in the equation of the correlation coefficient, which is right here. So we have here a standardization step in. Remember, the standardization step is basically that you take a difference between an individual score and you're summing these differences up and you're dividing it by some marker of variability. So the standardization basically equals, as we remember, individual score minus mean divided by the standard deviation, right? So it's a difference divided by a marker of variability. This is basically nothing else. You build a product between two deviations. You're summing all these products up and you're dividing it by the square root of both sum of squares. So you're dividing a difference, the product of a difference, by the product of two markers of variability. Thereby, you get a standardization step in there. This standardization step has ramifications because now everything evolves around the mean of X and Y. So that's the center of your entire focus. So when you utilize now correlation in its continuation of regression, actually, that's the best graph. What you do is you're using your data and you try to fit the linear model now through your data. And this linear model is basically, we have heard of this linear model already by calling it the line of best fit or trend line in Excel, or it's a regression equation. It's a linear equation that basically allows for us to describe the population or the sample population. We're getting to the R squared. Let's focus on the line first. The R squared is a little bit more complex because you try to use the regression for prediction, and the R squared is kind of a marker of that accuracy of the prediction. We're getting to that. But yes, it comes when we click on trend line in Excel. That's true. Okay, so this line of best fit is basically fit through our scalar with a caveat, because you have here a mean of X, which is somewhere shifted there, the mean of Y, which is somewhere there. Logically, right? Because you have the standardization step again. So that line of best fit goes through where these two means are meeting. So if I make a vertical line through the mean of X and a horizontal line through the mean of Y, which the horizontal line of mean of Y is basically our null hypothesis in correlation, where these two meet, that's where the trend line is going through. Per definition. So if we're aiming now to look at regression, we have with regression a tool to predict with this line of best fit, with this trend line or regression function, regression line, whatever you want to call it. You can predict individual Y's utilizing that line and a known X. So you're interested in one particular X, and you mean to try to predict predicted Y. You're doing that with your regression function. And you're doing this basically with the standardization step. You basically have now with the R, the possibility that you calculate by multiplying it with the standardized x, you get a standardized y hat, a standardized predicted y. So that is that association and this dynamic, how you can calculate that, is actually super important. So this is where that standardization step of the R is super important, because it merges the standardized x and the standardized y and connects those arithmetically. So this is basically, this calculation for the example we're going to do today. So we can now, the correlation coefficient of the example we're going to work with is 0.58. So if you have a set score of the predictor variable x of -2, and you multiply that by 0.58, you basically get to -1.16. So basically, this is this association that is depicted here, but also indicates that you have a regression to the mean, and the mean, as we know in standardization, is 0. So this is where these two are meeting. So this is the mean of x and the mean of y. So this is mean of x, mean of y. They're meeting exactly where they're crossing, if you make them horizontal and a vertical line. So, but we can still utilize this to build a good regression equation that allows us to do some simple predictions. And we will do this today, utilizing the data that I have shared with you on Canvas. So I included on Canvas this Excel spreadsheet, and I also included, not this, the back depression score. So that's actually, I like old papers. And so this is a paper from the 60s, I believe. This is the original back depression inventory score publication from 1960. That basically was the first attempt to really quantify, utilizing questionnaire items to quantify depression and the risk of individuals to actually be currently in a major depressive episode. It's still one of the most commonly used depression scales in the world. So it's, yes?
I have a question, a little bit off topic, but
let's speak after class, okay? Yeah. Okay, so the back depression inventory score is basically, and now remember the psychometric, and this is what is also an important publication to share with you, because you remember how we did psychometrics in last class, and we looked into different items and whether all these items point in the same direction and actually accurately predicting what they meant to predict to determine reliability. And you have the split half reliability and internal consistency. So this is how you have to think of those items. And these items all have to point towards the same outcome. Then you have a reliable tool at hand. And if you want a valid tool, you need to look at these items, see what these items basically predict, and associate this with various other outcomes that may be associating with depression in that way. For depression, it's a little harder because it's harder to quantify. Good. Okay. So back depression inventory. So the hypothesis here, or the research question here is, do stressful life events associate with depression? Do people with more stressful life events have higher levels of depression? So we have data of 10 individuals that are basically shown here in these lines. So if we just select now column B and column C, this is here again. We're just selecting these three. We go on insert and we go on scatter plot. That gives us a scatter plot. So if we're zooming in, zoom in a bit. Zoom into the scatter plot a bit, we can make it a little bit more pretty. So that's the BDI score as a function of stressful life events. We can now basically label the X and Y axis. We're going to chart design, a chart element. Horizontal line is stressful life events. Life events, it's as a count. We have on the y-axis, we have a chart element vertically. This is the BDI. This is the BDI score. So if you look at this, we see already, yeah, hypothetically there's a little bit of an association, but let's fit this, let's fit the trend line through it just to make sure that there's no association. If we're fitting a linear function through that, indeed, there's an increase in our y, our dependent variable, with an increase of the independent variable. So the more stressful life events, the greater the depression score. Yes.
What like is the main difference between say a correlation and regression? If regression is like to see if different variables have like a pattern, what makes that different than just the correlation?
Well, correlation is just describing the association and the strength of this association, whereas regression brings this on the next level. So we're utilizing in regression this equation. This one. We're using this equation. So this comes from correlation, right? That is our correlation. So this is what we did in chapter 15. That is just describing the association, and then we can do interpretations on our correlation coefficient. We can test for significant, whether there's a significant correlation or not. And then we're utilizing this correlation to basically go now towards prediction. So the clear difference here is correlation describes an association and the strength of this association. Regression uses this association and basically predicts an outcome or predicts a dependent variable utilizing independent variable. In a univariate setting, it's only with one independent variable. In a multivariable setting, you're predicting a dependent variable utilizing several variables. And we will get to that at the end of this class. Yeah? All right, thank you. So, okay, so we have started now this exercise here. So we have now our association. So hypothetically, the goal here is to predict our y utilizing these x's. So in the end of the day, you want to use this tool to predict an individual's depression score based on the number of life events. So you work in psychiatry or neurology, and you have a patient come in, and you suspect he or she may have, based on the symptoms, he may have a depressive episode. And you basically, you ask the individual, okay, so how many stressful life events have you experienced? And the patient starts telling you about his life events. And there's, yeah, my goldfish died, and I don't know, somebody stepped on my toe. So there are a lot of stressful life events that basically made him more likely to be depressed. And then you utilize this to basically depict that BDI score. So this is what you essentially do. So, good. So this being said, the first thing you need to do is you need to establish whether there's an association at all between these two variables. So we know how to do that. We have done that. So that's just calculating again our correlation coefficient. So that is y minus my. That's just the same. Yes.
Like, shouldn't there be like a range, like what should be allowed to be like stressful life events? Because I feel like that like changes it.
Can you repeat that, please?
Like, shouldn't there be a range of like what's considered a stressful life event for like this specific example? Because like imagine somebody were to go to it and like list like reasons that shouldn't really be reasons, but then you're writing about it and saying that this is considered a special like a stressful life event that's not really like the population, not really general. Like how could that like be statistically like proven? It's just based off of one person and like.
So there are a million responses to what you just said, and yes, you're right. You're absolutely right. But the problem that I personally have to answer this now, yes, you would need to quantify how stressful is the life event. And it's a fascinating question. But also when it comes to these, how should I say, it's not really, it's less objective, right?
You quantify this, that's not, probably quantify this in an objective way.
That is the problem, right? It's like you can't quantify something objective, which is subjective by definition. If somebody fills out a questionnaire and says, like, I'm depressed, you can't really. So the example here raises a million questions, obviously, because it's, well, I tried to be funny and I brought up the goldfish that died. It's like, it can be a traumatic event for people. It's like for a child, this can be truly dramatic, right? It's like, so you need to see these things in perspective. And usually you would need in psychology, and I'm not a psychologist, but I do have a strong interest in psychology. In psychology, you really need to base it on what that patient is telling you. If you ask specifically the question, what was the most recent traumatic, stressful life event that you had, or how many stressful life events you have experienced, that patient will guide you towards your answer. And what you really need to do, you need to listen. You need to listen and try to empathetically understand, why was that stressful for that individual, and why is he suffering? Is he suffering, and is what he's suffering from right now because of what he has suffered in the past? So it is hard, but you can't really objectively define, okay, so that is a stressful life event. And then the patient tells you a stressful life event that was stressful for him, and you're like, yeah, come on, that's not stressful. You can't do that, right? It's very subjective. That
Right,
is.
but then, so could this be taken and like assumed for like the general population of like?
Well, that's inaccuracy of prediction is particularly in a science like in psychometrics. It's tough. On scientific terms, it's extremely complicated. But what you really want to quantify is kind of that burden that this patient carries around. If that individual, no matter how you would perceive that stressful life event, but if that individual carries around the experience of 5 traumatic events that were really traumatic for him, although you don't consider this as being something traumatic, that patient will suffer from that. And you, in the end of the day, you just want to have a deeper understanding of, why is this patient not feeling well right now? Why is he not getting out of bed and he hasn't left his house since 2 weeks? So it's a good question, and I agree with you. It's like definition is the most important thing. Definition of outcomes and definitions of independent variables predicting those outcomes. The more objective they can be, the better it is. But it is just in an example like that, it's very hard to quantify. But yeah, it's a good question, and very valid question actually. But it's tough. Okay. So number of stressful life events, whatever it was, back depression inventory is going, and it's the same with this outcome, right? The back depression inventory score is like, that's what I meant with like, you need to validate these questionnaires. There's so much variations how people answer these questionnaires. There are differences in culture, different cultures, different ethnicities, different socioeconomic levels. You need to factor all of this in. And that's actually from and this is also why psychologists, they actually, if you want to become a psychologist and you want to do research in psychology, you need to be top notch in stats. I have learned survival analysis from a psychologist, and he was top. So there's a lot of methodology coming out from psychology, because they are facing very challenging question where objectivity is very hard to obtain, or very hard to establish. Okay, excellent questions. Everyone, good flow. Okay, so we have back to stressful life events and BDI. So we have, first we need to calculate the deviations, and the deviations is basically x minus mx. First we need an mx, so we need mean. And so we always start with characterizing our populations, which is always with Markov central tendency and Markov variability. We have an average of these 10 people, and we have the standard deviation of these 10 people. So we see already, and that's no. So we see already quite some deviation in terms of the life events, and we see quite some deviation also in the BDI. And oh no, I deleted my, oh no, there it is. So just to feed in your point again, is like A is not only, so now I can't let go of it, thank you. So we basically were seeing all this variability. But what feeds into your point is like the perception and the reaction to life events, which is the, it's not only the perception, it's also the coping mechanisms that we have. It's social network, social support. There's like a million things come into play. You see the variability here, right? Not that this is really data, but it's accurately depicted. So people react differently to individual life events. So and that's kind of feeding into your argument, right? It's everybody reacts differently. There's no clear definition, so it's tricky stat. Okay, so but back to our deviations. We're not philosophizing too much. Okay, so we have x minus mx. That's a simple one. We do x minus mx. We need to log in the mx. We do y minus my. We're logging in the my. We're creating the product. As we remember, this is how you basically start off. Which is basically the product of these two. Now we can just pull this all the way down. So that's our numerator. Basically the sum of these 10. So just to refresh, no, not this. Oh, we can also bring it here. So just to keep in mind, this is basically what we want to calculate now. So we have the sum of the products of the deviations divided by the square root of the sum of squares. So this is where we're going with this calculation, right? So we're basically x minus mx, y minus my, product of these two differences. Now we're basically calculating, secondly, our denominator. For that, we need a sum of squares. So this is this and this squared. Now we need this squared. We need this squared plus here. Plus here. Now we need the sum of these two, and our denominator basically is the square root of the product between sum of squares x, sum of squares y. So denominator is now the square root of this multiplied by this. So that's the denominator. And this is now calculated as the r by basically taking the numerator. Oops. Oh. This divided by the denominator. So we have an R of 0.58. So that was the example where we can, which we've seen before. So it's basically, it's the same. Correlation coefficient. Good. So now we know now from the previous slide, was it on regression? No. So we know from here that we're calculating now our predicted y, set y hat. So we have this internal standardization. The standardization that comes in because we have a difference, a product of two differences, summed up, divided by the square root of the product of two sum of squares, x and y. That's basically the same as standardization as we have done it with x minus mean divided by standard deviation. So we basically have a difference and we're standardizing by our variability. So what we're essentially doing here is like we have the standardized parameter where we remember from the regression to the mean where our set score for x is 0, our set score for y is also 0. So that regression line goes exactly through where those two lines met. And this we're using now to calculate our standardized set y hat and the standardized set x. You remember how we're calculating our set, which is x minus mx divided by standard deviation. If we want to calculate this backwards, we're doing set multiplied by standard deviation plus the mean. So this association we're bringing now into regression by using the standardized x's now to calculate our standardized y's. So if we're calculating now x for where x equals 0, 0 life event, 1 stressful life event, 2 stressful life events, and 3. First, we need to calculate our set x. So set x is now calculated as set x is calculated now as x minus the mean divided by our standard deviation, right? Oh, yeah. X. So we're doing this in a bracket and we're dividing this by our standard deviation. It basically gives us here a standardized x for x equals 0. So if we're standardizing our x equals 0, we're getting minus 1.14. If we're doing the same exercise now, so for that we need to log this in. If we're doing the same exercise now for all the other x's, we basically have our standardized x set x values. So now it's simple, right? So we know now that set y hat equals correlation coefficient multiplied by our set x values. So now set y hat, we can now easily calculate as this multiplied by r. And if we log this in, we can exactly just again put this all the way down. So this is our standardized y hat. So this is literally our prediction across all the axes of interest, but standardized. And to get it from standardized back to a predicted y, a raw y, we need to now have set y hat. And remember the equation, how we're standardizing it, x or y minus my divided by the standard deviation. So now we need to do set y hat multiplied by the standard deviation plus the mean. And that's how we get back to the original raw score. So this is m5 multiplied by our standard deviation plus an m. Now we're logging this in. We can do this for all the other ones too. So what does this mean now? Oh, good. Let's bring this. Yeah. So if we're zooming in now, and we're looking at the regression function now, so we have now 9.5 where x equals 0. That's pretty much here. And then we have 12.8 for x equals 1, then we have 60.2 for x equals 2. And then we have 19 for x equals 3. So this is basically how you build this regression equation out. And now if you remember, we did the exercise in last class. We looked into what are the components of a regression equation or a linear equation of a line. We have an intercept and a slope. So if we're applying this now to our use case of a regression equation, we basically have y hat, that's our predicted y, equals intercept plus slope multiplied by x. And so now the intercept we talked about, the intercept is where x equals 0. So we know the intercept already, which is 9.542. And the slope is easily calculated. If you remember the equation, it's y2 minus y1 divided by x2 minus x2. You can also do it easier because you have here increments of 1. So you can save yourself the x2 minus x1. You're basically just calculating this minus this. And that's your slope. That's how simple it is. So now your final equation is basically nothing else but y hat equals 3.241. So, 3.241 multiplied by x plus 9.542. So that's your regression equation. That's all there is. That's all you need to know. So that's considerably simple. So now we can test our. Now we can test this by basically asking R to show us the equation. Or Excel, it's 3.241 plus 9.542. Good. So that's how simple this is. Okay, so that's regression equation. Now we have. Okay, intercept of the line is A, B is the slope. We're calculating the set score, we're multiplying the set score with the correlation coefficient, and we get this back to a raw score. We know all of this. And we get the equation for the line. We've done that, line of best fit, yes. So the problem with prediction is predictions have errors, quite a lot of errors, notably, because we remember that there are always those unknown unknowns, invisible variables, not quantified, not accounted for, not included in prediction. You get a little better in your prediction by including additional variables. That's what you do with multi-variable regression. But for these examples, we're doing the first step at this point. But basically, predictions are full of errors, and the margin of error is factored into this regression analysis. That means it's contained in the accuracy of your prediction. You have to measure this somehow. So if you have data, you have a certain accuracy that you see based on your data, the real data, and your equation and your line. But you have to quantify how good the prediction really is. And you're doing that by quantifying the standard error of your estimate. Standard error, same situation. So you calculate that error from your prediction line to your individual point, with the idea to be able to have a quality criterion for your prediction. And you want to understand which of these two predictions is better. Like intuitively, just when you look at it, everybody is going to gravitate out saying this is just the worst and this is better, because the points are just not as far away from the line than on the other graph. So we are in need now to have a metric that allows us to quantify the accuracy of that prediction. And that is a metric that you know already from ANOVA. We knew it then as R squared or eta squared. Now it comes back again as R squared. That hasn't changed. But if you remember R squared with ANOVA, it was the proportion of variability that was attributed to the variance between the groups as a function of the total variance. So now essentially we're going a step further and we're quantifying the amount of error that was removed by not using a prediction against the mean, that you say, okay, so I predict my individual y value by just fitting a mean through that. So y equals mean of y. I tilt that and I fit it through the intercept. And now the proportional reduction of error is basically how much closer are my values now to my prediction. That's in broad terms how it works. So you basically calculate this proportion of error that you have removed by shaping a line with a line equation rather than the mean. That's essentially what the R-square is in the context of regression. And that's how it's calculated. So we have a sum of squares total, which is the sum of squares of y that we've calculated already. And that's the denominator. So that's our absolute total variability. And then we have the fraction of that we mean to quantify, which is the sum of squares total minus the sum of square error. So that's the leftover error. So we're seeing now how much that equation actually has explained. And we're calculating this in a second. Okay. Okay. So back to this. So we know now the sum of squares y, we know already. That's this one. So that's our total variability. That's the total error. Because the y minus my is basically quantifying the error if you would have used a flat line. That is your total variability. That's your total error. If no, we don't want that. So if you want to calculate now a residual error, and there's a really good graph here. So this shows what we're going to calculate now. This is the error y minus my. Each individual y subtracted from the mean. And this is now what our regression error is. So this is basically the distance from the regression line to the individual point. It's called the so-called residual. So the residual basically gives you an idea about this distance, how much better your prediction got. So for that reason, we just need to calculate y hat, but we need to calculate y hat now for each of our participants. And that we can do quite easily because we know intercept and slope. So we just need to calculate our x multiplied with our slope plus the intercept. So that's now of the first individual, the estimated predicted and predicted depression score. So that's how you can do this prediction. So you calculate that x for individual one multiplied by the slope plus the intercept. And if you lock this in, you can basically do this for each individual. So now you have estimates for each of your 10 participants. And now in the next step, the only thing you have to do, you need the error now. You have now the predicted error. And now you need the y minus y hat squared. And this is basically y. Oops. Y minus y hat squared gives you now your residuals. So these are the 10 residuals. And now the only thing you need to do, you need to sum those up. So that's your rest error. So what you want to do now is calculating the R squared And I'm doing this right here under the R. So this is now sum of squares, and sum of square minus sum of square of the regression divided by the total sum of squares. And that gives you the R squared. So that's the proportionate reduction of errors. So this is how much your regression function has improved your prediction over just using a mean. And if we confirm this now in Excel, we're going to see now that this is consistent with Excel, 0.33. Okay. Of note, if you just take the 0.58 and you're squaring this, you get the same value. Do not do this when you have more than one variable. In multivariable regression, this is not permitted. Gives you a different value. R square is calculated differently because if you have an additional variable and you have, let's say half of these are diabetics and the other half are not diabetics, you get two different levels. You get two regression equations. It basically parallel shifts it by either being diabetic or not. As an example, you can also have additional variables, then becomes a little bit more complicated, but basically that's the gist of it. Okay. So this is basically, excuse me. Thank you. So this is basically how you calculate this proportional reduction of error, also called coefficient of determination, or also just R squared. So good. Problem is regression to the mean. We talked about mx and my. The R is going right through that. That standardization will pass through that cross point. That means that every regression equation will always gravitate, or not gravitate, go through that cross point. That means if you have a mean, it will always regress to the mean. So with whatever prediction you mean to do, it will always regress to the mean. That is sometimes a little problematic, as we have seen with our example of in the correlation chapter. It's regressing to the mean. And then it's basically regressing towards outliers because they have a lot of weight. And that leverage they are exerting on the model will basically change the slope, which is in regression analysis actually a statistically diagnostic tool for the accuracy of the prediction. Okay, so now we go back to this. Okay, regression to the mean occurs when extreme scores tend to become less extreme. That means if you utilize, and they bring here a stock market example in, well, here, they bring a stock market example in because in the stock market, you basically, you're trying to predict the future, right? So you build various regression models. Of note, one of the more popular ones on the stock market is the so-called ARIMA, which is an autoregressive model that basically uses dynamics from before time point 0 and utilizes those, regresses those, and basically uses those to progress forward. But I'm not qualified to talk much about it. Otherwise, I would be driving a nice car. So you have these time predictions, and if you have extremely high values, they will gravitate towards the mean because same concept applies. It gravitates towards that cross point between mean of x and mean of y. So here it's shown with stock market example, basically where you have high values gravitates towards the mean. That's what they mean to illustrate with that. So that's in the prediction. Limitations are usually with regression that the data it's not strictly true, because you can use regression models to analyze data from randomized controlled trials, and then you can have then you use it to analyze randomized data. Then you can establish causality, but one of the problems is you cannot establish causality with a correlation and analysis, except for when you use it on randomized data, which you don't do in most cases. The independent variable is usually a scale variable. Yes, doesn't have to be a scale variable, but that's beyond the scope of this class. And limitations in predictions are like those found in correlations. Don't establish causality. All right, any questions? If not, have a nice evening. See you on Monday. Thanks, Daria. Any questions from your end?
Just a question about
I don't hear you.
Oh, can you hear me?
Oh, wait.
Can you hear
Can
me?
you say it again?
Can you hear me?
I still can't hear you. Sorry. Well, hold on.
Wait,
I
can you
need to
hear me now?
change my.
Can you hear me now?
Okay, now I should hear you.
Can you hear me?
Yes, now I can hear you. Sorry about that.
No worries. Just a quick question about the practice lab number 4. In the instructions, it said that it should be we should look at module 20 and 21, but chapters 15 and 16. But chapter 15 and 16, no, it said chapter 13 and 14, but chapter 13 and 14 is in chapter 15 and 16. I mean, module.
Yeah, I mixed up module and chapter. I look into that. I'll revise it. Thanks for bringing it to my attention.
Okay.
Thank you. All right, sounds good.
Okay, bye.
All right, have a nice evening. Bye-bye.
Thank you. Have a good night.
Thank you.